This is in your book 9-2, where you're doing a hypothesis test comparing two means. Now, there are a lot of situations that can happen when you're comparing two means. First situation is, do you know sigma 1 and sigma 2? Right? Do you know the population mean, population standard deviation for both populations? The second situation is, are they unknown, right? Do you not know them? And then the third situation is sigma 1 and sigma 2 are unknown, but assumed to be equal. Now, the more common situation, obviously, that's an L. The most common situation, obviously, is this one. And then maybe you see this one too, where you can assume the standard deviations for the populations are assumed to be equal, and then you could change the methods that you use to deal with comparing the two means. But you guys are not going to deal with anything but the second one. So if you're comparing two means, you're not going to know sigma 1 and sigma 2. And you're not going to assume them to be equal. They're going to be unknown, which means you're always going to be using t-scores and the student t-distribution as long as you're comparing two means. Okay, if you're doing one mean, that's different. As long as I'm comparing two means, you guys, you are only on the t table. Sigma 1 and sigma 2 are unknown. You're only dealing with this situation. So you're now there's more than that, but only this situation. Now outside of that, okay, so sigma 1 and sigma 2 are unknown. So we're always using t-scores. Outside of that, there are two cases. I'm only going to do with one case today, but the first case, are the two samples dependent? Two samples or populations. Are they independent or are they dependent? Independent or are they dependent? The two samples or populations are dependent. So when we talk about dependent samples, oops, I'm spelling that wrong. Depend, oh my God. I'm not spelling properly. Dependent. If we say that two samples or two populations are dependent, then we call them, we say we have matched pairs. So typically with matched pairs, you have before and after cases. You have husband and wife cases. You have one person and you're comparing the left arm to the right arm. You could tell that they're dependent. Independent, let's say you're comparing, men versus women, things like that. They're separate, independent cases. So the first one that we're going to do, at least right now, is the first case where I have two means I'm comparing. The standard deviations for the populations are unknown, so that means I'm always on a student t-distribution. And I have independent samples. They're not dependent, they're not matched pairs, they're separate. So that's where we're starting. Under all those conditions, if I want the test statistic or the p-value, my calculator trick will be something. And then, or if I want the confidence interval, my calculator trick will be something. Let's go to the calculator, see if we can figure out, because this is what you're going to have to do, right? Figure out what we might use. So stat over to test. Now, if I'm running a test, so these are all the test things. Z-test was what we used when we had one mean with sigma known. T-test was what we used when we had one mean, sigma unknown. So obviously I'm going to use two because I'm not doing proportions now. Is it two sample Z or two sample T? Well, we don't know sigma 1 and sigma 2, so we're doing two sample T-test. Okay, so let's write that down. Two sample T-test. If you want the test statistic or the p-value, right? Because remember that, two sample T-test. Because remember that when you do the stuff on the calculator that ends in test, it gives you a test statistic or a p-value. So then that means if I scroll down to the interval stuff, again, Z interval was when I wanted a confidence interval for one population mean and sigma was known. T interval was when I wanted a confidence interval for a population mean and sigma was unknown. So obviously I'm going to use two. I'm not in proportions. Is it sample Z or sample T? Well, you guys don't know sigma 1 and sigma 2, so it's two sample T int if I want an interval. Right? So, I mean, it kind of tells you If you go into the calculator, you forget what you use, you can kind of analyze it and remember anyway, because it's not really that hard to figure out. 2 sample t int. So int for interval, test for test statistic or p-value, right? Okay, so let's see. Yeah. 2 sample t int. Okay. All right. Let's do this one. So I have this situation here. Let's see what I have. The nice thing is sometimes you'll see everything given to you, which is awesome. But let's go here. So what do I have? I have this data set 7 in Appendix B list full IQ scores for random sample of subjects with low lead levels in their blood and another random sample of subjects with high lead levels in their blood. So if you think about that already, they are independent, right? One group has low lead levels, another group has high lead levels. Not the same person comparing the level, before and after. It's 2 completely different scenarios, so they're independent samples, independent populations, okay? Use a 0.05 significance level to test the claim. All right, I'm comparing low blood levels to higher, right? Now, they didn't tell me which one was sample 1 and which one was population 1, correct? So I'm going to label that myself, and then that will help me with my notation when I write out my null and my alternative hypothesis. And it doesn't really matter which one is which. So just call this 1 and this one 2, which means that this is N1, the sample size for the first group, which is represented by low blood lead levels. X1 bar is the sample mean, right? X bar is the sample mean for the first group, which in this case represents the group with low blood lead levels. S1, notice it's S and not sigma, right? I don't know the standard deviation for the population. This is the sample standard deviation for the sample. Sample 1, low blood lead level group. And then, so these will have subscripts of 2s, okay? So this is the sample size for the second group, which is represented by the high lead level, and then the sample mean for that group, and the sample standard deviation for that group, okay? So once you label that, now I could write everything else. So be careful with that. You want to remember what the heck is group 1 and what the heck is group 2. Use a 0.05 significance level, that's alpha, that's just straight alpha, to test the claim. Let's write the null, and let's write the alternative. That. So let's see what the heck. The mean, I'm comparing a mean to a mean, not a proportion to a proportion. So I'm comparing, if I want to write that down now, mu1 to mu2 somehow. Mu1 to mu2. Now for my situation, what do they represent? Mu1 is the population mean for the population of people that have low blood lead levels. Mu2 is the population mean for the population with high blood lead levels. This is the sample stuff. This is the population stuff. Compare the mean IQ score of people with low blood level. That's the first. Oops. That was my group 1, right? That's what I labeled as group 1. So test the claim that the mean IQ score of people with low blood lead levels is higher than the mean IQ score of people with high blood lead levels. That was 2. So is group 1, is their mean lower than group 2? So what kind of test do I have? Is group 1, is their IQ score, higher, sorry, higher, not lower, higher than the other group? Is it higher, greater than the other group? And then the null would be equal to. So what does this mean? Do the people with low blood lead levels have higher IQs than the people with high blood lead levels for the population? That's what this alternative is saying. And notice it's matching the verbiage here. So when I write my interpretation, I could just kind of go straight there. Now, another way to represent this is to say, the difference, right? If I say the difference, if I subtract 2 numbers, if I say 2 numbers, their difference is 0, then that means the 2 numbers are the same. If I say a difference between 2 numbers is greater than 0, that means that I'm subtracting 2 numbers and their difference is positive. That means that the first number has to be bigger than the second number in order for this to be true. Otherwise, it wouldn't be positive, would it? If the first number is less than the second number, then I would have negative outcomes, right? 2 minus 3 would give me negative. 3 minus 2 would give me positive. So saying that the difference is greater than 0 is also the same as saying that the first number is bigger than the second number. So you might see it either way, but they mean the same thing. But they're both telling me that it's a right-tailed test. They're both telling me it's a right-tailed test. All right, so if I want to, actually, I'll just straight up draw my rejection region now. My rejection region's in the right tail. Since it's only one tail, alpha's all in there, critical value, one critical value. I'm going to just find everything. So we're going to find the test statistic. We're going to find the p-value. And when I want a test statistic or a p-value, I use, in this case, right, the calculator trick that ends in test. I'm comparing two means. I don't know sigma 1 and sigma 2. They're independent samples. So I'm doing 2 sample t test, right? Ending in test for test statistic and p-value. Let's find the confidence interval also, which I would use 2 sample t int, right? And then we'll determine the confidence level in a second. The critical value, this is not a standard normal distribution curve. This is a t-distribution. So your critical value, I'm going to write it bigger here, is a t-score, which you can use inverse t if you have the calculator trick, or you can use the table. Now, if you're on a t-distribution, that means that you need degrees of freedom. And so if you have 2 samples, how do you determine your degrees of freedom? You're going to take the smaller value between them. So that means, so the degrees of freedom, let's say for the first sample would be 77, one less than the sample size. And the degrees of freedom for the second would be 20. 20 is less than 77. So the one that I'm using here is 20. So for you guys, when you have, 2 situations, you need to determine what your degrees of freedom are. Take the smaller value between the 2. Subtract 1 from the sample size and take the smaller number as your degrees of freedom to find your critical value. Okay, good. What else do we need? So, once I settle this up, then I'll find everything. Let's determine how do I find the confidence level? Where's that? The confidence level, right? So is it a 2-tailed test or is it a 1-tailed test here? It's a right-tailed test, right, because of the greater than sign. Yep, points to the right. So this is a 1-tailed test. There's only one rejection region. So I'm going to do 1 minus 2 alpha to get my confidence level. Go back to my thing. So my confidence level, let's just go straight here. Confidence level is 1 minus twice alpha. So 1 minus twice 0.05, which is 1 minus 0.1. which is 0.9, which means I'm doing a 90% confidence interval. So this is all the stuff that I need. I can do my calculator stuff now. So I'm just going to go straight there and find all this info, and then we'll interpret it after. So let's look at my calculator. And since I'm already here, what do we say? We said 2 sample t tests, right? Because I don't know the means. There's 2 of them, and they're independent. Enter. Again, I could have data, which means that I would have lists of data values that I would have to input first, but I don't have that. This time I have stats, so that's cool. So let's go back to my information, and we said X1, N1 was from the low blood lead levels. Let's try to say that 5 times. So X bar 1 was, okay, so don't input this incorrectly. 92, so wait, 92.88462. SX1, the sample standard deviation from the first, was 15.34451. And then N1, what was that? 78, I think. Yeah, 78 was 78. To the second group, the second mean was 86.90476. Don't enter that wrong because that would suck. The second standard deviation was 8.988352. And then the second sample size was 21, right? We have a right-tailed test. Oops, go back up, right-tailed. Make sure that's highlighted, right? Right-tailed test. You guys are always going to be no on pooled because you're not assuming that the standard deviations are equal. So you guys are no for your independent cases where sigma 1 and sigma 2 are unknown. And so you'll never have to change that based on what you'll be given. Boom. First thing is the alternative hypothesis. The second thing is the test statistic. The third thing is the p-value. This is degrees of freedom using a formula, which you guys don't have to worry about. Then you can just check and verify that this stuff that you input was correct because you already have this information. If you had two lists of data, though, two data lists, then this would also give you the sample mean and sample standard deviation if you need that. You wouldn't have to calculate that. This gives you that, but you don't have that. You were already given that. So, but anyway, I'm just pulling the first two things from here because that's what I want, the test statistic and the p-value. The what? There's a formula that is used to calculate the whole degrees of freedom for this whole thing, but you guys don't deal with that. So in a sense, you're approximating it with safety because you're taking the smaller version of the two. You don't have to deal with that whole thing. But, you know, it does a different calculation for you guys. You're not using it, so don't worry about it. Let's do the confidence interval. It was a 90% confidence interval. So let's go back down to ints, right? The int stuff. So 2 sample t int, and this should already be input, right? The C level was 90%, so 0.9. And then again, no for pooled because of your situation. They're independent samples. You don't know sigma 1 and sigma 2, and they are not assumed to be equal. And calculate. And it does this. Again, it gives you all this stuff too, but you only need the first information for now. Confidence interval, which is, we're going to go 1.596 on the low end and 10.364 on the high end. Okay. And again, you guys can see this, right? My confidence interval, if I'm comparing two means, represents the difference of the two means. The difference, subtraction. So if I were to go to the populations and take the mean or average of low blood levels in the population, and then the mean average in the high lead levels, and take the difference between those two values, that is what this represents for my possibilities. Critical value, forgot the critical value. Do I have inverse? Yeah, I have inverse T. Those of you that have inverse T, you can use that. Those of you that have, do you guys have your tables? If you use your tables, inverse T, area, what is the area? 1 minus 0.05. And then degrees of freedom, what did we say, 20? And then, so 1.725 was my critical value. So if you're using the table, it should match that. Let me see if I can find the table real fast. I didn't have that up. So 1 second. If you're using the table, real quick, I think I can find that fast. If you're using the table, go down to table A3 where you're dealing with T stuff. Where is it? Here, right? T distribution, critical T values. Your area in one tail is 0.05. You have 20 degrees of freedom. So I'm on this row, right? In this column, 1.725. You get the same thing, okay? If you're using the table versus the calculator. All right, so now let's come to our conclusion, and I could do obviously multiple different things. If I compare the p-value to alpha, the p-value is less than alpha, so that looks like I reject. The test statistic is in the rejection region because it's bigger than this critical value, which is here, so it's in the rejection region, so I'm rejecting the null. So based on those, I'm rejecting the null. Let's look at the confidence interval method and see if that matches. So this interval has all positive numbers. 0 is not in here, right? Because we're seeing if the value on the null. So the value on the null is basically saying that the difference is 0. 0 is not in this interval. So it's not a possibility for the population. So again, we reject the null. So this is all looking good. It's all matching. So everything is saying to reject the null. So if I'm rejecting the null, hold on, I'm going to pull this up so I don't have to. I'm rejecting the null. So there is sufficient evidence to support the alternative, right? So I'm just going to pull that from this. The alternative states that this is bigger than this. So that matches here. The mean IQ score of people with low blood lead levels, the mean IQ score of people with low blood levels is higher, greater than, the mean IQ score of people with high blood levels is higher than the mean IQ score of people with high blood levels. Oh, high lead blood levels. Blood high. Low lead blood levels. Okay. Okay, so again, I'm rejecting this. So I'm supporting this. There's sufficient evidence to support the claim that mu1 is bigger than mu2. What does that mean? Mu1 is the population mean from group 1 here. Low blood levels. Their mean IQ score from that population is bigger than the mean IQ score from this population, which comes from the high blood levels. That's why it's so important to define group 1, group 2 initially, so that you understand what the heck all this means, because you have to convert it back into words. You have to go back and forth between words into notation and then back into words, interpreting what the heck you just did. So it's very important that you know what the heck the variables mean.